then just before you start, always just introduce everybody in the team because some folks are online and some are here and some are mixed teams. So it's just useful so I know who everybody is on the team. Yeah.
Yeah. I mean, on the team, it's just me and Ayan, and Vishnu
Got
as
it.
well, and some other people on Discord helped us with some ideas.
Yeah, that's
But
right.
for the presentation, it's mostly just me and
It's
Ayan.
just the two.
Yeah. I'll just share my screen.
Okay, and I'm gonna time today. So your
Alright.
timer is clicking.
Alright. Go ahead. Can you share see the thing?
Yeah, we can see the screen. Just do full screen mode.
Yeah.
Yeah. Can you see it properly now?
Yeah, perfect.
So the problem that we set out to solve was the problem of dealing with more and more extreme temperatures, especially in states in northern India, where the summer temperatures are reaching above 45, almost 50 degrees in some places. And we wanted
So
a
50
way
degrees
for
Celsius, just
people
so that.
to deal with these extreme temperatures when they don't have access to electricity. And they're often the most vulnerable populations are people who work outdoors, like outdoor laborers and construction workers. So the solution we are working on was a sort of a tent. So just a quick by the numbers. In the last 10 years, 2001 to 2019, India recorded almost 20,000 deaths. And as you can see in the graph here, you have about anywhere between 1,000 to 2,000 deaths every single year due to heat stroke, which is the red curve. And they are increasing every year. And the most vulnerable populations are 30 to 65-year-old men, especially. And the distribution across states, Telangana and Andhra Pradesh are especially vulnerable, as well as Punjab, UP, and Bihar. And the majority of these people are either agricultural workers or construction workers. And several studies have been done to try and find out what exactly is the largest threat to them in terms of heat stress. And some studies have found that essentially wet globe temperature which is a combination of various environmental factors, humidity, radiant heat, and air temperature, can explain over 2/3 of the variance in terms of heat stress and metabolic rate reduction. So our aim would be essentially to reduce this wet globe temperature. So like I said, there are many different sources of heat that affect an outdoor worker, and we'll be focusing on reducing the things that contribute to wet globe temperature. So the problem that we're trying to solve is essentially we need to create an affordable, portable, easy to assemble device that outdoor laborers can use to protect themselves from heat by lowering the temperature and without relying on any electricity or external energy source. And I mean, the biggest thing that heat mitigation, the best strategy for heat mitigation when you are in a hot environment is essentially to remove yourself from the environment. And you do that by finding shade. So OSHA's recommendation for any outdoor labor is water rest shade, WRS. And these three things have been shown to be the best ways of reducing the risk of heat stroke. And essentially, passive rest in just being outdoors and resting is not enough. You also have to rest in a cooler space. And taking frequent breaks in a cooler space has been shown to significantly improve heat stress recovery. So how do people deal with it currently? Currently in India, I mean, the pictures on the top and on the left here are things that many of us might have seen. Construction workers will often build these metal tin shacks, which absorb a lot of heat, that are not very structurally sound. They're not very well insulated either. In the summers, they can absorb, and essentially the internal temperatures can shoot up almost in a threatening manner. Then you have these tarpaulin tents, which are makeshift, and They are tend to have a very short lifetime. They're not very durable against wind and rain. And then the better solutions in terms of thermal insulation would be like UNHCR has a series of portable tents. And while they are good at solving the earlier problems, they are usually very expensive, costing up to $400-700. And they're also fairly hard to assemble because they have lots of parts. And unless you have someone who knows how to assemble it, it's not easy to do. So yeah.
So this is our condensed thread path. We have a more detailed version on the website, but these were the main things that we took out from it. The requirements were that we wanted it to reduce the temperature by around 5 to 10 degrees. We wanted active cooling without electricity. We wanted it to be lightweight and for it to be carryable by one person, because we wanted to focus on the target demographic of mostly daily wage workers who don't really have who go to work every day in a very hot space and don't really have shade or places to rest at, and homeless people as well. There's also, we wanted the cost to be less than 3,000 for it to be affordable. So there were certain design parameters that we had listed out, and there's some analysis of. So we wanted to basically use an origami collapsible structure design for it to be lightweight and portable. We have some sort of evaporative cooling that we'll discuss later on, and we have we are going to use reflective coating over the outer surfaces, and there are some risks and countermeasures listed as well, which we'll address later on in the slides as well. So just going to our solution. So this is basically cardboard Gami's tent that we are adapting to the Indian context. So cardboard Gami basically made this tent for the context of the US, and it's made out of cardboard, and it's an origami collapsible tent, and it folds up into that structure, as you can see, and it unfolds and can hold anywhere from like 1 to like 5-6 people, depending on the size. So there are some things that we want to change for the Indian context for it to help combat heat. Essentially, because cardboard is not number one water resistant, so we wanted to change the panels to be reflective as with being white colored, and we wanted the panels to be made of corrugated plastic, which have a slight air gap, which would help with insulation as well. We wanted some ventilation system, which we'll discuss in the next slide. Compact fold and stuff like that is already present in the design. And we wanted some sort of evaporative cooling as well, which we'll discuss soon. So this is the prototype. We folded some prototypes. I think we have them.
This is the design is Crizzling, right? This is the Crizzling origami, right?
This is
the Crizzling is here.
The Crizzling is for a more conical collapsible structure, something like this. These are called the Yoshimura fold.
Okay.
Yeah.
So this is the prototype that we made just from paper. And we did some math to calculate how much each panel would need to be. So it came out to be around 70 centimeter to 18 centimeter, 70 centimeter base and 18 centimeter height for each panel. This is for a 1% tent. This can, of course, be adjusted based on size.
And we arrived on this number because of...
So we arrived on this number because there's actually, we experimented with some angles. So this was another prototype we did. Essentially, there's basically a trade-off between angles and the space that the tent will inhabit, like the tent will let someone inhabit. So if you have a very equilateral triangle type design, you will essentially have a more compact folded structure, but when you open it, there won't be as much space inside. On the other hand, if you decrease the angle and you have sharper angles, then you have more space inside, but it won't be as compact when it's folded up. So we can't keep, you get diminishing returns as you keep increasing the angle, decreasing the angle. So this is how we landed on this sort of angles and stuff. And
So we realized that one of the issues with this design was that it's entirely enclosed from two sides, and the only openings are in the front and the back. So one thing that you're losing out is ventilation. So we found this method of essentially increasing ventilation entirely passively, which takes advantage of this phenomena called the Venturi effect, which is that if you force air through a narrower gap, the speed of the air would increase. And in Bangladesh, people have made this thing that they call the eco cooler, which uses bottles, and you can mount this on a window. And essentially, the breeze from the outside, as it passes through these bottles, as they pass through the holes, they speed up, and that essentially makes the breeze stronger on the inside. And over here, I mean, we found a study where some people had seen the effect of wind on the inside and the outside of a tent, and they found that on the top is what it looks like when the doors and windows are closed, and versus when the doors and windows are open. So ventilation does have a significant impact on the internal temperature inside the tent. So we wanted to do something similar to this design, but it would have to be on collapsible as well. So how do we make this sort of conic structure collapsible? And that's when we came upon these Crestling cone design, which we also made a prototype of. So it essentially has a wider opening on one end and a smaller opening on the other. And you can choose what your radius of the openings should be. And based on that, you can determine how much the air will speed up. So for a triangle of a certain size, we said that, say, we can fit 5 circles across it, each 2 centimeters in radius. Then based on the external breeze, we can give it a 4-fold increase if we give it these dimensions, a 4-centimeter inlet size. And yeah, so this is the cost breakdown that Arjun went through.
Yeah, just one more thing. And there's like
Yeah.
5 of these fit on one panel. So we also wanted, so we don't want to do this on every panel, of course. We wanted to do it on
Right.
opposite panels, so that there's some crosswind.
So that would look like on these rows of triangles, which are up here. Since they're angled at different angles, you'll have multi-directional ventilation. So depending on which way the wind is blowing, you can get ventilation in pretty much every direction through the tent.
Yeah. So here's a cost breakdown. I'll go over it quickly because we don't have much time. So there were some sheets that we basically took up some prices from online, and we determined exactly how much sheet material we need. We calculated the cost. We wanted the hinges to be based from like canvas fabric and resin to like glue the hinge together. And there was some extra cost for some of the cardboard cones. So this is one last future scope of the project, which I'll just quickly go over. Essentially, the idea for this was because the wind will just speed up, so it will provide ventilation, but not cool ventilation necessarily. So we wanted to add the cooling effect of the air as well. So we thought of basically what you use in a cooler, in a evaporative based cooler, which is basically an aspen wood, like a jute layer of some sort, which has some moisture, and the cool breeze blows through it and tends to cool the room by evaporation. So basically, we wanted to attach it to one of the panels, and then have the cones outside. And this is what the diagram basically of it looks like. And
so
yeah,
this would have to be like an external attachment. So that's why, I mean, we're still trying to figure out how we can attach it in a way that allows it to be not too much work to put in, but also it continues to be a collapsible design.
Yeah. And these are our references. And in the interest of time, I'll just let the challenges be here. But yeah, I think that's mostly it.
Okay, that was 15 minutes. So we have 7 minutes for questions. So loads and loads of questions people should ask. I love the Bangladesh reference that you guys found. That is absolutely fantastic. In terms of context of thinking about what's already working, how do you adapt it? So can you say a little bit more? Is there a way to think about evaporative cooling, especially with the water side of the story integrated? Has any experiments been done when you started with the water bottles, I was starting to think about that. Oh, maybe there is a moisture holding capacity in that. So in that experiment, there was absolutely no, it's only a Venturi effect. That's
Yeah.
it.
Yeah.
So over here, I think they had all they had done was the Venturi sort of thing, but actually we did find
Is
we
there
did
some
find a
references that you
bunch of
guys have
people.
on the evaporative side of just how far
Yes.
you could go? Yeah.
So people have made like these sorts of coolers. I don't know. Can you see this?
Yeah.
Yeah. So these have like on the inside, they've sort of made like a mesh which has water on it, and then
Yeah.
they're passing the air with a fan through the mesh, and then it has the Venturi effect. So then you're essentially blowing cool air out.
I
So
see.
we figured that it would be better if the mesh is on the narrower end, so that after the wind is sped up, then it is passing through the cooling mechanism. But that would mean that you'd have to put it on the inside of the tent.
Yeah.
So we were thinking that we could create like a sort of a slot mechanism, which
Yeah.
could you could essentially wet the mesh and then fit it into a slot on the inside
And
of
are
the
there
tent.
any numbers on the evaporative? Because I could imagine that the jump between evaporative and purely Venturi would be a big number. Have people calculated
Did
just
we look at that?
I don't think there's a number on evaporative plus the Venturi effect. I feel like we did find some numbers of so just this plain so this one. So just this
I just
model
want to get a sense, can you hit the 10 degrees C? 10 is a pretty big number to think about. To go
yeah.
from 50 to 40 or even 30. And
Yeah.
so the question is, can pure evaporative cooling actually achieve
So
it?
there's
Or is
a
there any data set to show that?
it's a bit of a double-edged sword because the wet globe temperature is actually a combination of things like humidity
Ah,
as well as air temperature.
I
And
see.
in a small enclosed space, if you were to add evaporative cooling, you might inadvertently end up increasing the humidity as well.
Oh, that's a
And
really good point. I
that
see.
that might have a sort of a negative
Yeah.
effect on heat stress.
So
see.
just the plain version of this, I think we read in some papers that it was quoted that it could reduce the temperature up to 5 degrees. I don't
see.
think there's a number for this plus the evaporative cooling because I'm not sure if it's been done before. At least we couldn't find any.
Yeah. So I mean,
Yeah.
those are some sort of tests that we'd have to do.
What you just said implies that there is an optimization curve that you guys
Yeah.
should try plotting. I think everything else fits the picture, but it would be valuable to say how much true ventilation versus humidity. Because in a tent, of course, humidity is one thing. Of course, shade is a big part of the puzzle. But I love what you said that if there is a true design parameter, it's valuable to think about where is that design space of how much humidity can you bring in evaporative cooling in a closed space like this.
Yeah.
So kind of trying to do that calculation more quantitatively. Other questions? Yeah.
Looks like there's a little flexibility with the price range. Have you looked into maybe heat reflecting paint or different materials like that you could coat the exterior of your panels with?
So we figured that honestly, where's the heat cost right now? Now here. We figured that I think if we used white panels, that it in itself would be a fairly like it would reduce the heat in a
There
reasonable.
are these Mylar sheets that runners use after marathons, and Mylar is quite inexpensive. I think it's valuable to think a little bit about going extreme on that reflective side of the story. But then again, you should do it as a factor of a calculation. Because remember, 50 to bringing it to 40 or 30, like that's a 20 degree, and it might be that you need to do multiple things to get to that point.
Yeah.
So I wouldn't rule out, and Mylar, I don't think it's a calculation that you guys should do. And I'm assuming it's Mylar. You guys know what is that thing that you get after running? If you run a marathon, my intuition is it's to cool the body, right?
I think it's the opposite. I think it's to keep you warm.
Is it to keep you
Right?
warm?
Yeah, I think it's like
No.
a wind blanket.
Really?
Yeah, it is.
You know, after marathons, when you get this reflective thing, I always thought it's because you are so hot. Or is there a totally new function?
It is Mylar.
It is Mylar, right? That I knew.
And it's to retain your body heat.
Oh, it's to
and
retain
prevent
heat.
hypothermia. Okay.
But that's kind of confusing. Why is
Why
it
is it
reflective?
I think
Oh,
my
it's
intuition is for the
reflective on the
wind.
inside, so it retains your radiative
Oh.
heat.
Yeah.
That's pretty interesting. So it would still work in this context.
Mhm.
It would still be true. But I think there is the absorption ratio you have to think very carefully about because there is radiative in the IR versus also visible
Yeah.
light.
Yeah.
Hmm.
And you might get a difference between the two because it might be the radiative heat that it's holding. Other questions?
I think that we did like a sort of a back of the envelope calculation for how much heat is coming in via radiation and how much would each form of mitigation contribute to the reduction
Yeah.
in temperature. And I think reflective accounted for more than 50% of it. So I think working on that
I see.
is a good idea for sure.
I see. Yeah. There's a question from Ben who studies origami. Maybe if you pop it again, it's in the chat.
Yeah.
Can you repeat it?
Yeah.
Yeah, so is panel deformation a concern for the degree of expansion you're aiming for? Cresseling and Yoshimura origamis both require the individual panels to deform slightly from the flat state to a curved one for the full structure to expand. Aside from the hinges, do you have any thoughts on mitigating accumulating damage in your plastic or cardboard panels from repeated panel bending?
Yeah, I think a little bit about just stress patterns that a tent would see, either wind and other factors. And what Ben is referring to, this is called the flat foldability problem. That the only reason these things can exist is because they tend to give curvature to your sheets. So your sheets are in stress state. And I think maybe one way he's also hinting towards the solution is some of that stress can be taken on by your hinges. I really love the idea of a fabric hinge in origami because my problem with origami structures and cardboard origami has this huge issue. You cut these incisions, and of course, that's the weak point, and they all break exactly where you made the hinge. So this idea of making hinges from another material can mitigate that. But I don't know have you guys played with it a little bit? If you have elastomeric hinges, what are the other things to mitigate some amount of stress? Because you want the tent when it's folded, and if it's under a wind stress, you want some plasticity of the shape to change. You don't want it to blow away, which is the big issue around tents to begin with.
Yeah, I think one of the advantages of this Yoshimura design is that you never have multiple folds on the same point.
Yeah, that's not compounding.
It's not compounding. So every fold only has 2 layers on either side of it, and that sort of means that you don't you can make this as long as you want. And you won't have any additional strain or stress building up in your structure.
Yeah.
But I think you do have to think a bit about how to keep the panels from maybe bending. I think over time.
Yeah, I mean, just in a utility of a tent, you're going to see all kinds of environmental factors. Even for tents, for example, in tent design, the most common first thing people think about are anchor points. And so now going beyond, this is just an object that's kept. How do you really anchor it? And is there a right kind of anchor point to, it might be that the first panel and the last panel have a slightly different architecture that it allows for anchoring. It allows for, I think you can go beyond the core structure is there, but it's useful to think about anchor and stress patterns.
Right.
And what is the easiest way to make sure that in different crosswinds, this can actually survive as a tent?
I think the main anchor that we came up with, I mean, we didn't come up with, but what Cardboard Gami uses is basically a floor at the bottom of this. I think we didn't fold it with this, but there's essentially a floor that is put. And then if you keep any weight on that floor, it does anchor it to some extent. But I think we can do something better if we try.
Yeah. Okay, I think we're out of time. Any other burning question? Otherwise, we're going to switch to the next team. This was awesome.
Thank you.
Thank you.
Do you know who goes next?
Yes.